Welcome everyone. I'm Norman Wahlberger. Today in this course on elementary mathematics, we're going to look at addition. Addition in practice, especially with numbers which are relatively small in the range 1 to 10. So in our last video we talked about this addition table, which encodes for us all possible additions between numbers 1 to 10 and numbers 1 to 10. So for example, 7 plus 9 is read off in this table by going across that row and down that column and giving us 16. So 7 plus 9 equals 16. And I mentioned, perhaps mischievously, that this 16 could also be named in a slightly different, more logical way by calling it 10-6, because that corresponds more clearly to what it actually is written in the Hindu Arabic form. 10-6, same as 16. And I did also point out that there were a couple of interesting features about this table that were worth noting. The diagonal is particularly important, as we're going to see today. We're going to be talking about those numbers. They're rather special. Those are the even numbers. They're appearing down the diagonal. And this cross diagonal is also important. Okay, so we want to have some practice now at getting students to learn this table by using it to solve problems. And while it might be a little bit tedious for students just to be given lots of examples, what is 3 plus 5, what is 4 plus 6, and so on, it can be a little bit more interesting if we're asking the students to add together three numbers. Geometrically, if we had this number 4 and this number 3 and this number 5 and we're adding them, then in terms of the rectangles, we're just pushing these three rectangles together to form a longer rectangle. But officially, we actually only add two rectangles at a time. So there's in fact sort of two ways of actually accomplishing this, by first shoving those two rectangles together and then that combination, or first moving these two rectangles together and then combining that with the first one. Of course, either way we get the same result, which by the way is 10, 2. If we peel off 10, 3, 4, 5, 6, 7, 8, 9, 10, then that 10 there is replaced by this red square in our kindergarten format and 2 left over. So arithmetically, with the Hindu Arabic system, there are really two possible ways of bracketing this kind of relation. 4 plus 3 plus 5 can be interpreted in at least two different ways. We can think about first adding the 4 plus 3 together, which is 7. So then we'll get 7 plus 5, and then 7 plus 5 is 12, or 10-2. So this requires two lookups of the table, or we don't really be wanting the students to be looking things up. We want them to know what the sum is. They need to know what 4 plus 3 is, and then they need to know what 7 plus 5 is. However, the same sum can also be interpreted this way, where the instruction is to add 4 and the sum of 3 and 5. Well, the sum of 3 and 5 is 8, and then 4 plus 8 is 12, or 10-2. So in both cases we're getting the same number, which is reassuring, and this can reinforce the idea for students that they're doing things right. If they end up getting the same answer with this kind of question, then, well, very likely, not necessarily, but very likely, they will have been doing things correctly. And of course, this little exercise is valuable because it reinforces the associative law. This is actually a law, a rule that is valid in general. And it's something that eventually students have to recognize as being an important and useful law. If we have any three numbers, L, M, and N, say, then L plus M, first evaluated, and then adding N, is the same thing as adding L to the sum M plus N. This is just a fancier way of writing this phenomena here in a more general form, with letters replacing particular numbers. So this associative law is a good source of problems, and here are a few little exercises that illustrate that. So we can be given a sum of three numbers, say 3 plus 2 plus 6, and we can ask to compute it in two ways. And then check, of course, that the result is the same no matter which way you do it. Or 6 plus 7 plus 4, or 8 plus 1 plus 9. And of course, you could easily make up a lot more, as long as we sort of require these numbers to be small enough so that the sums still stay in the range between 1 and 20, or 1 and 210. Here's a more sophisticated application of the same idea, but now with four numbers. Suppose we want to add 2 plus 3 plus 7 plus 4. And without changing the actual order of those four numbers, we can combine them in a lot of different ways. We can calculate 2 plus 3, calculate 7 plus 4, and then add those two. So what is this actually? 2 plus 3 is 5, 7 plus 4 is 11. And so then we have to calculate 5 plus 11. Do we know how to do that? Well, actually not exactly, because that's outside of the table that we calculated last time. We had 5 plus 10, so 5 plus 10 is 15. But I hope that it's not too hard to see that if 5 plus 10 is 15, then 5 plus 11 is going to be one more, namely 16. So the connectivity and the pattern that the table exhibits is important in going beyond it. Another way of calculating this would be to rearrange the last three numbers and sort of calculate them first. And we could do that by having a 3 plus 7 there, calculate that, and then add 4 to that, and then finally add 2 to that. Or we could do 2 plus 3 first, and then add 7, and then add 4. Or 2 plus the sum of 3 and 7. All of that plus 4. So working out any one of these combinations will involve different intermediate steps. But the final result should, of course, be the same, because we're really just taking four rectangles and we're pushing them together in different ways, thinking about the order in which we push adjacent rectangles together as being variable. Here's another exercise related to this last question. How many different ways are there, in fact, of computing this sum by arranging brackets like I've done up here? Here I've got 1, 2, 3, 4 different ways. Can you think of any other ways of arranging the brackets? How many ways are there altogether of arranging brackets? The associative law involves 3 or possibly more numbers added together, where the order of the actual numbers isn't changing, but the order of the combinations is different. Either that combination first and then add that one, or this combination first and then add that one. Remember, there was this other law, the commutative law, that had to do with actually changing the orders of the two numbers. So we can combine these two things to generate some more problems. For example, this exercise to show that 8 plus 5 plus 6 is the same as 8 plus 5 plus 6. That's exactly an associative law application. But this one is different because it's taking this thing here and using the commutative law, the fact that 8 plus 5 is the same as 5 plus 8. So we're rewriting it. So here we're generating some more combinations by allowing ourselves to swap the orders of the numbers themselves. We're sort of mixing them up in different ways and combining them with different brackets. So these kind of exercises show that young learners can generate their own problems to work on. And by checking that the numbers that you get in all cases are the same, they can in fact check that they've understood things correctly. So here's an exercise related to this. How many different ways are there, in fact, of combining these three numbers, say 5, 6, and 8, in all possible ways, these being some of them. Can you think of some more ways of adding them together? And a variant on this, how many different ways are there to sum the numbers 3, 3, and 7? It's a little bit different than this case because here the two of the numbers are the same. These are a little bit more challenging questions. As you become more familiar with arithmetic, you start to distinguish between different types of numbers. All numbers are no longer all the same. Some numbers have certain properties, others have different properties, and some numbers are sort of similar to other ones in certain ways, and other numbers similar to other numbers in other ways. A very important example of that is the distinction between even and odd numbers. Very important distinction. So the numbers which appear down the main diagonal of the addition table have a special property. They're the numbers that we get by adding 1 plus 1, or 2 plus 2, or 3 plus 3, all the way up to 10 plus 10. And those numbers are, in order, 2, 4, 6, 8, 10, 10, 2, 10, 4, 10, 6, 10, 8, and 2, 10, or 12, 14, 16, 18, and 20. Well, those aren't all of the even numbers, but those are the first ones. And here they are written out in a row. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 2, 4, 6, 8, 10, 10, 2, 10, 4, 10, 6, 10, 8, 2, 10. They're the even numbers. And the list, in fact, does keep going. The other numbers, the ones that aren't on this list, are the odd numbers. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Or 1, 3, 5, 7, 9, 10, 1, 10, 3, 10, 5, 10, 7, 10, 9. And of course, they keep on going too. So this distinction between even numbers and odd numbers is a very important one in mathematics. Another way of describing the even numbers is to say that they are the multiples of 2. By that we mean that they have the form 2 times n for some number n. For example, 2 times 1 is 2. And here's the rectangle that encodes that. This is a 2 by 1 rectangle which has 2 squares in it. 2 times 2 is 4. There's a 2 by 2 rectangle with its 4 squares. 2 times 3 is 6. There's the 2 by 3 rectangle. 2 times 4 is 8. There's the 2 by 4 rectangle, and so on. So the even numbers are naturally associated with rectangles that have 2 rows. If you have a rectangle with 2 rows, then the number of squares that it has will be an even number. The even numbers are useful for counting by 2s. So counting by 2s means, well, we ignore the odd numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, etc. So for example, if we wanted to count all these little stars here, well, we could do 1, 2, 3, 4, 5, 6, and so on. That's the usual counting by 1. But a slightly more efficient way, once you're used to it, is to count by 2s, which involves pairing them up. So that involves a bit of work. So there's one pair, there's another pair, there's another pair, and there's another pair, and there's another pair, and so on. So we count them off by pairs, and as we do so, we count by 2s. So let's do that. 2, 4, 6, 8, 10, 10, 2, 10, 4, 10, 6, 10, 8, 2, 10. 2, 10, 2, 2, 10, 4, 2, 10, 6. There's 2, 10, 6 stars. Let's check that with more standard notation. Maybe we'll work this way to see if we get the same answer. 2, 4, 6, 8, 10. 12, 14, 16, 18, 20, 22, 24, 26. Now if you're going to count a long ways by twos, then you will end up finding that you do this. You go 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. 2, 4, 6, 8, 30. 2, 4, 6, 8, 40, and so on. So that's a bit more advanced. Let's just practice counting by twos. Perhaps you can, for example, count the number of letters in a paragraph or something like that. You'll see that counting by twos is more efficient than counting by ones often. The odd numbers, 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, are also separated by twos. Going from one to the other is a case of adding 2, just as it was for the even numbers. And if we think of all of the numbers, then as we go through the numbers, they're alternating odd, even, odd, even, odd, even, odd, even, odd, even, and so on. Here's a little exercise. What digits do odd numbers end with? For example, this odd number, 13 or 10-3, ends in a 3. So that's the number in the ones position. Remember, this is the ones position, this is the tens position. So we're interested in what are the digits that occur in the ones position for odd numbers. And same question for even numbers. So that's a very useful thing to be able to do, because then if you have a bigger number and you want to know whether it's even or odd, well, it turns out all you have to do is look at the last digit. The last digit tells you whether it's even or odd. Odd numbers also have a geometrical representation, which is not quite as clean as the even ones. So here are the odd numbers represented in a reasonably useful way. There's 1, 3, 5, 7, 9. In each case, what we have is we have a rectangle with 2 rows, and then we have one more square sticking out from that. Which makes sense, because an odd number is one more than an even number. So if we took that even number 6, which is that rectangle there, and then we added one more, we're going to get 7, which is an odd number. If we add one more, then we get the next even number to fill out a proper rectangle again. Okay, so here's now an important rule that tells us what happens when we add even and odd numbers. It turns out that whenever we add 2 even numbers, we get an even number. Whenever we add an even number and an odd number, we get an odd number. Whenever we add an odd number and an even number, we get an odd number. And whenever we add 2 odd numbers, we get an even number. So notice the result here is even here and here along that diagonal of this little square, and the cross diagonal elements are both odd. So a natural question that you should be asking when presented with a statement like this is it true? And then a second question, once you've kind of convinced yourself that the answer to this first question is yes, is why is it true? Can we see or can we understand the reason for why such a statement is true? Well, in this case, it's not too hard. So let's first try to determine whether this is likely to be true or not. Let's look at some examples. So here are some examples of addition taken from our addition table, or maybe we've just computed them. 1 plus 1 is 2. That's the case of odd plus odd equals even. 1 plus 2 is 3. That's odd plus even equals odd. 1 plus 3 is 4. Odd plus odd equals even. While 6 plus 4 equals 10, that's a case of even plus even equals even. 3 plus 7 equals 10. Odd plus odd equals even. Here, 8 plus 5 equals 13. That's even plus odd equals odd. And 4 plus 10 equals 14. Even plus even equals even. So, at least from these limited examples, it seems to work. So why is even plus even an even number? Well, we can explain that geometrically, because we've seen that an even number geometrically is represented by a rectangle with 2 rows. So here we have 2 rectangles with 2 rows, and so when we add them together, we can add those 2 rectangles together, and we're going to get a bigger rectangle still with 2 rows. That's even, the sum is even. How about even plus odd is odd? Well, there's an even number, which again is some rectangle with 2 rows. And here's some odd number, which is a rectangle with 2 rows plus 1 more. Well, when we add those, the 2 rectangles with 2 rows are going to combine to give another rectangle with 2 rows, in this case that one there. And this little leftover square is still going to be left over. So even plus odd is odd. And the same thing happens if the order is the other way around. If we have odd plus even, we're still going to get odd. First of all, you could say that's because of the commutative law. But if we want to think geometrically like this, there's an odd number with a rectangle with 1 more. There's an even number, which is just a rectangle. When we combine them, well, they don't fit together so well. We may have to chop this little extra fellow off momentarily. So if we do that, then the 2 rectangles can fit together. And then we can add this thing on at the very end. So the result is still an odd number. And finally, this one here, odd plus odd is even. Why is that true? So here's an odd number. It's a rectangle with some extra additional square. Here's another odd number, another rectangle with 1 additional square. How do we add those 2 together? Well, we may have to think about removing this square temporarily and moving this rectangle together with this rectangle to form that rectangle there. And then this extra one here can come and join this extra one here, can sit right on top of it to make a nice rectangle with 2 rows. So from 2 odd numbers adding together, we get an even number. There's another exercise you might want to check some more examples just to make sure that this really is true. So we can summarize that even and odd rule business with a simplified addition table. In this addition table, there's only evens and odds. So evens and odds is one possibility, evens and odds as another possibility over here, and here are the 4 possible alternatives. So the way we read this is that an even plus an even is even plus odd is odd, odd plus even is odd, and odd plus odd is even. This is like the addition table with numbers, except that instead of having 10 numbers down the side here, or 10 numbers across here, we only have the 2 types, even and odd here, and the 2 types, even and odd here. Then there are only 4 possibilities instead of 100 different possibilities in that former addition table. Alright, so that's good. We've gotten some more practice with addition. Of course, very fundamental, basic operation. Next time we're going to talk about multiples. We've talked today about multiples of 2. We're going to talk about other kinds of multiples, like multiples of 3 or 4. It's also very important. And we're going to have to deal with this issue of names. What do we call numbers which are bigger than 20? What are the names for larger numbers? So that's what we're going to be doing next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.